This is a lecture on substrates, which is part of a course on fundamentals of micro and nano fabrication. Any micro and nano fabrication starts with a substrate because that is where you make your integrated circuit or structure on. It's very important to understand the properties of that substrate and specifically how to choose one, how is it made, and how the choice of a substrate affects the properties and the eventual application. So, let us get started. So, this is our agenda. We will go over what is a wafer, why is a substrate called a wafer in the first place. We will briefly discuss the various materials that are available. As you will see, while there is a lot of materials possible, for most applications a very small subset of materials or substrates is enough. Then we will go into details of how those wafers are fabricated, because only when we understand how the substrate is made can we truly appreciate its properties, what is hard about it, and what is so special about these substrates. We will also go through some jargon to actually understand how the wafers are specified. So, if you were to purchase a wafer tomorrow, you may need to specify certain properties, and what those properties are and what the jargon means is something we will go over, and we will finish off with an understanding of how to relate the properties of the wafer to the eventual application, so that you can given an application you can better understand what type of substrate you will need. So, what is a wafer? As the name suggests, wafer is a thin substrate on which the micro and nano fabrication is done. The name comes from historical reasons. Here is an example of a silicon substrate, and you can see that it looks like a thin slice of wafer, and that is why the word wafer. Typically, it is 200 to 2000 microns thick. This thickness is decided either by a standard or mechanical considerations or electrical properties. So, it really depends on what application you are. A little note on what I mean by mechanical considerations. As the size of the wafer kept increasing, for example, here you are looking at a 2-inch wafer and a 4-inch wafer, the stresses involved at the edges on the wafer also became more important. So, there is a possibility that the large wafer, if it is very thin, will break. So, larger wafers tend to be thicker, smaller wafers tend to be thinner. In general, wafers come circular in shape. The reason for that would be obvious in the next few slides. It is a consequence of the way we make the wafer. But you can also purchase wafers in square shapes, and certain specialty wafers also come in square shape for very specific reasons. Typically, these wafers are given a mirror shine. So, again, if you look at this image below, it has a shiny surface. You can actually see some I think a lighting fixtures reflected on top. And that is because when you are doing micro and nano fabrication on top of these substrates, it is very important to have a smooth surface, because any topology will also be reflected in your eventual structure. So, it is giving a flat surface gives you the best chance to accurately reproduce a micro or nano structure. Finally, the most important point. These substrates are remarkably pure, much purer than what a typical material scientist or chemist would call pure. If you were to purchase a chemical, 99.99% or a 99.999% chemical is considered extremely pure. It turns out wafers for micro and nano fabrication, especially those that need to be used in electronics, have to be much purer than that. The standards are much higher. Routine silicon wafer that we use in our lab can often be parts per billion pure. Okay, so, this is one of the purest materials we know how to make, irrespective of any industry. Okay, silicon is one of the purest materials we know how to make. As we'll, in the next few slides, it will become more clear how do we actually achieve this remarkable amount of purity. So, here is what are the various materials that are available. So, the workhorse for most micro and nano fabrication is silicon. So, if you notice on the right, you see a small part of the periodic table. So, you are looking at group 4, which is carbon, then below that silicon, germanium and tin. Below carbon, silicon is the workhorse, as I mentioned. However, the general class of those 3 materials, which is carbon, silicon and germanium, all can be considered semiconducting. In fact, the first semiconducting device was demonstrated on germanium, not on silicon. as you go from carbon to germanium, the band gap reduces. This is not a course on electronics, so I will not go into detail of what band gap means. But for now, it's sufficient to say that that going from carbon to germanium is essentially means going from diamond to single crystal silicon to single crystal germanium, and the reduction of band gap has certain implication for its optical and electronic properties. Now, chemically speaking, you can achieve the same number of average bonds. If I were to stress the definition of an average bond, but the same number of essential bonds if you, instead of taking a group 4 element like silicon, take one group 3 element, for example gallium, and one group 5 element which is arsenide. So, the gallium arsenide is also a semiconductor. Now, you can extend this further to a whole family of what is called 3,5 materials, for example aluminum nitride, aluminum phosphide, aluminum arsenide, aluminum antimonide, etc., and similarly with gallium and indium. These are typically called 3,5 materials, and they are often used in optoelectronic applications. We will go into details later. Now, taking the same concept further, we can again make a similar sort of looking material by going to group 2 and group 6. A good example of that would be zinc oxide. Now, zinc is strictly speaking not a group 2 material, but it does have an oxidation state of 2. So, zinc oxide can be thought of as a 2,6 material. Similarly, cadmium sulfide, cadmium oxide, cadmium arsenide are also semiconductors. All right, moving on. But this is just the start. A semiconductor does not just have to be a binary. Like gallium arsenide, it can be a tertiary or a ternary, and all of that leads to a bewildering variety of substrates you can actually purchase commercially these days. With the arrival of 2D materials and perovskites, the sheer number of semiconductors that you can purchase as substrate has actually increased significantly. But in most cases, those substrates are only useful for niche applications. They tend to be extremely expensive, hard to make, and available in very small sizes. So, by and large, if you are getting started in micro and nano fabrication, you tend to look at silicon, 3,5s, oxides, etc. Let us go into detail of silicon. It is the material that is used primarily in the IC industry, which basically means all chips. If you are using a laptop to look at this presentation, you are using a silicon chip. You are using a mobile phone, you are using a silicon chip. If you are using internet, it is backed up by circuits that are based on silicon chips, etc. So, silicon is used to make both CMOS and BJT type of circuits. If these words are not familiar to you, do not worry about it. This course does not go into details of CMOS or BJT. Just you should understand that most of the circuits that you know, most of the microchips that you know are probably based on silicon. Not beyond electronics, another very interesting aspect of silicon, it has very extremely good mechanical properties. Here I am just comparing some typical mechanical properties of silicon compared to steel and aluminum. And you would notice it has the same Young's modulus or elasticity as steel. Its yield stress is extremely high, it is very strong, its density is low, which makes the structures light, and its thermal conductivity compared to steel is much better and is almost as good as aluminum, which is a metal. So, these are a remarkably good mechanical properties, and what this has allowed us to do is to make microstructures that are also mechanical structures. So, this has led to the proliferation of these MEMS and NEMS types of devices, where you do not have where the goal is not an electronic device, but the goal is a mechanical device. As I sort of mentioned before, by and large silicon is the most mature platform that we have. If you are starting in micro nano fabrication, that is a good place to start. Next, let us look at gallium arsenide. This is the most popular 3,5 material. Great advantage of gallium arsenide in general in 3,5 materials is that they tend to be a direct band gap material. What that means is, optically speaking, they are much more efficient in emitting light than silicon. So, gallium arsenide is often used in LED type of applications. So, any LED that you have seen which is green or red in color or somewhere in between is probably a 3-5 material based. Gallium arsenide also can tune. A gallium arsenide family of semiconductors also exist. For example, aluminum gallium arsenide or indium gallium arsenide or ilium gallium arsenic phosphide. And this family of materials has a range of band gaps, and getting a range of band gaps is again very important in optoelectronic applications, because the color of the LED is directly related to the band gap of the material. Gallium arsenide and general 3-5s also have very high mobility. So, if you look at the table below, compared to silicon or germanium, which are elemental group 4 semiconductors, gallium arsenide and indium gallium arsenide have much higher electron mobility. So, these materials are often used when very high mobilities are required, and you form these high electron mobility transistors, which are called HEMTs. Gallium arsenide is also used often for RF applications, which has strategic implications such as radars, solid state radars, etc. So, a very interesting material, very interesting optoelectronic properties. The only problem is it's significantly more expensive than silicon, and by and large it has been it has played a second fiddle to silicon simply because it is so much more expensive and harder to make it. We will discuss some details on why is it so hard to make gallium arsenide compared to silicon, or harder, not so hard, but harder than silicon. Then let us here is a list of other semiconductors that we can look at. For example, sapphire. Sapphire is aluminum oxide. It is an insulating substrate, which is important in certain applications. It is also the substrate that is used to grow nitrides. Gallium nitride has become an extremely important in semiconductors, and a lot of the gallium nitride HEMTs are actually made on sapphire. It also is a very hard material. If you remember your hardness scale, sapphire is right below diamond, and that allows the use of sapphire as window materials where you want some scratch resistant windows. So, in high end watches, for example, sapphire wafers are often used. Another interesting material, elemental semiconductor, is germanium. As I think I mentioned earlier, germanium was actually the material on which the first transistor was demonstrated. Unfortunately, it has certain problems regarding its oxide, which is why silicon became more popular than germanium in the long run. However, germanium as a substrate is still available and popular. A very niche application of germanium is that you can use it as a substrate to grow 3-5s on top. So, 3-5s are not very compatible with silicon, but with germanium they are more compatible. So, back in the day when gallium arsenide substrates were very hard to make, a lot of the gallium arsenide work was actually done on gallium arsenide that was deposited on top of the germanium. Germanium also is optically transparent in the infrared, mid infrared, and it is used in that application. Germanium and silicon are miscible. So, you can form alloys which are called silicon germanium, and those alloys have found a lot of use in HEMT, or sorry, HBT, which is a faster version of the silicon BJT. Next is silicon carbide. Again, this is an alloy between silicon and carbon, which is a group 4 material. It is a very wide band gap material. If you look at the image on the right, you can see that the silicon carbide wafers tend to be transparent. That is indicative of their high band gap. However, the advantage with silicon carbide is also a very stable material. It can survive very high temperatures. The large band gap allows it to have to function at high temperatures. So, high power devices where you want to flow a lot of current, silicon carbide devices have become very popular. It is also a substrate for gallium nitride, just like sapphire was. Next is quartz. Quartz is silicon dioxide, but a crystalline version of silicon dioxide. It is related to glass in some manner, just like glass is transparent, quartz is transparent. The only difference between glass and quartz is one is amorphous solid and the quartz is a crystalline solid. Quartz is often used in photomasks. We shall go into detail what a photomask is later in some other lecture where we will do lithography. It is used as substrate for thin film transistors. It is often used in RF applications because it has very low losses, and often used in microfluidics, because a lot of time in microfluidics you want a transparent substrate. A cheaper version of quartz is glass, which is a substrate that probably you are all familiar with. It is a low cost material. We make a lot of glass, and glass can be shaped into these wafers that can then be used. Applications are OLED, thin film transistors, solar cells, displays for your mobile phones, for example, are made on glass substrates. And finally, plastics. They have become more popular lately. In general, plastics do not survive very high temperatures, which limits what sort of micro nano fabrication processes we can do on plastics. In fact, it's a research area to try to reduce the temperature of micro nano fabrication techniques so that they are compatible with plastics. As that research area has matured, so has the use of plastics. The common ones are Kapton, PET. Kapton is this yellow colored material that you see on the right. It survives a little higher temperature of around 300 degrees C, which is high enough to do a lot of fabrication and actually make electronic devices on it. So, yeah, so if you are looking at flexible, low cost, semi-transparent type of applications, plastics is a good place to start. So, with that general discussion of various types of common substrates that are available, let us go into a little bit more detail and how do you actually buy this. This is like the jargon associated with substrate selection. So, if you were to go and buy a silicon wafer today, you would have to specify certain properties of that material. So, here is an example of what a typical silicon specification would look like. So, first you have to specify the size of the wafer. This is the diameter. So, you can buy substrate that are 1 inch, 2 inch. Back in the day in 1960s, 1 to 2 inch wafers were the state of the art because it was harder to make larger area wafers. Since then, as technology evolved, we were able to make larger and larger areas. These days, this industry is standard at 300 mm, which is 12 inches, or 450 mm, which is 14 inches. Oh, sorry, 400 mm, which is 14 inches. By and large, for most research application, 4 inches is a good place to start. You then have to specify the orientation. Since this is single crystalline silicon, it has a certain crystallographic orientation. So, the face that you actually have, the flat face, what is the orientation of that flat face is what this orientation refers to. So, you can actually get 110, 100 or 111. We will go into a little more detail on what and how do we actually select the orientation or how do we orient the wafer. In general, 100 is the most popular. That is because it is the one that is used in CMOS and is made in highest volume. The next is grade. You can either select a prime grade, a solar grade, a test grade, or a mechanical grade. The grade comes from the amount of impurity. Grade refers to the amount of impurity in the material and how well it was made. For electronic applications, you typically want prime grade silicon. For solar cells, where cost is important and large bulk orders, bulk production is important, typically a slightly lower solar grade is used. Test and mechanical grades are only used when you do not care about the electronic properties so much. So, if you are doing some test where you just are looking at when you are trying to optimize a recipe for micro nano fabrication, or you have a MEMS application where the mechanical properties of silicon are important, but electronic properties are not, you may consider buying test or mechanical grade wafers. They will be significantly cheaper. How the silicon wafer was made or how the crystalline silicon was made also has a huge implication on properties. So, depending upon whether that method was float zone or Czochralski or microcrystalline, the properties differ. We will look at each of these separately in the next few slides. So, for now I will skip this. The next you specify the thickness. This is after all a wafer, and as I think we discussed earlier that depending on the application you can select a certain thickness. Solar grade wafers tend to be thinner, standard CMOS grade wafers tend to be a little thicker, and the thickness scales up as the wafers become larger and larger. Next is resistivity. This refers to how much doping has been added to the wafer. The concept of doping is often used in electronics. If you are not familiar with this, I would refer you to an earlier lecture where we went through what doping is. Doping changes the conductivity of the wafer, so the resistivity of the wafer. So, the resistivity of the wafer is what is specified. Typically, is specified in a range. You cannot have arbitrarily precise resistivity. Why? We will see a couple of slides later. You can typically get where resistivity is from which are very low, which means a very highly doped wafer, 10^19 doped wafer, which will be less than 0.005 ohm centimeter, to an insulating wafer, which would be around 10^5 ohm centimeter. Then there is a specification what is the finish. We discussed that often you would want a smooth finish on at least one face, so that is called a single side polished wafer. But for certain application you may want to make electronic structures on both the sides, in which case you want a double side polished wafer. On top of that, you can also get some amount of pre-processing done on the top of the wafer. So, if you do not have access to all the tools of micro nano fabrication, you can request vendor to do simple blanket depositions or simple blanket processings. Those are typically optional, they increase the cost, but are available. Now, to understand each of these specifications a little more, we want to go into the detail and understand how do we actually make a single crystalline silicon ingot. Okay. So, we start with what is called polysilicon. This is silicon that has been purified to 99.999%, which for most material or chemical applications is essentially pure. So, this is the purest silicon you can buy. It comes in chunks, and what you then need to do is convert this polycrystalline extremely pure but not pure enough silicon into a silicon wafer. So, first you do that by creating a single crystalline ingot. How do we do that? We will look into that in a minute. This ingot will have a certain orientation, will be typically single crystalline. So, it has only one grain, and and much purer than the grade that you started with. Okay. So, typically the ingots are 1000 or 10,000 times purer than the feedstock that you started with. Then you will shape this ingot into a perfect cylinder. So, you will cut off these beaks that you see in the ingot. So, these are cut off. You see these wavy patterns that are on the surface, these are smoothened out, and then on top of this smoothened cylinder, then you cut it into wafers. So, think how wood is taken, how a log is converted into round shapes. So, this is what is exactly happening. So, you have an ingot and you have these diamond wire saw, and that is just being used to cut it down into thin slices. The distance between the wire saw decides what is the thickness of the wafer. This sort of sawing leaves certain striations on these wafers, which are called saw marks. So, in order to get a smooth or mirror shine, then you need to polish these substrates. So, that is what is done in this etching and polishing setup. Now, let us go into the detail of each of these steps. Okay. So, first is making the ingot from the polysilicon feedstock. So, as we discussed, so there is a polysilicon feedstock that is 99.99% pure. Typically, this comes from something called a Siemens process. If you are interested, I urge you to go and read up about it on its own. There is a lot of information on the internet. The most common method of converting silicon feedstock into an ingot is what is called Czochralski method. It was developed by a Polish scientist, Jan Czochralski, in 1918. It is a generic method of making any crystal, but it is especially popular for making silicon. Today the technology has become extremely mature. So, if you look on the image on the right, we can now make ingots that are larger than a human and extremely large diameter. When silicon technology started, this was not possible. You typically would make ingots that are much smaller in size. Why is it more complicated to make larger ingots is something that will be obvious down the line. Okay. So, the basic mechanism of Czochralski method is given in this slide. So, you start by taking your polysilicon and melting it. So, you heat it up to above the melting temperature of silicon. Once it has completely melted, you can at this stage add certain amount of dopants. So, the amount of dopants you add will define the resistivity of the eventual wafer. Because you are dissolving it in a homogeneous solution, the doping that you would right now get in this melt would be hopefully uniform. Then you start with a seed. Now, this seed has a certain orientation. The orientation of the seed will ultimately decide the orientation of the wafer that you will get. So, 111 oriented wafer would require a suitable seed. So, you start with seed. Seed is typically a very small, hopefully single crystalline material. The size does not really matter as long as it is just small. So, you dip it in the silicon, this silicon melt, and start rotating it. Why do we rotate it will be obvious later, but simple answer is uniformity to make it more homogeneous. The rotation is actually what causes the ingot that eventually forms to be cylindrical in shape. Okay. So, this is why wafers are circular. So, you rotate it and you slowly pull it out. Effectively what you are doing is, as you are pulling it out, is you are reducing the temperature of the silicon that is in the melt, and it is freezing, but it is freezing while it is in contact with this single crystal seed, and because it is in contact with a single crystal seed, the silicon that forms is oriented along that orientation. So, as you keep pulling it, you continuously increase the size of that one grain. Okay, so, you form a single crystalline material and you keep rotating it, so you get a cylindrical shape. As you keep removing the material, the amount of the melt reduces, because of course, all the silicon has got into the ingot, and you continue this process until your melt is exhausted. So, what you have done is you have started with a polycrystalline pieces of silicon and converted into a one single ingot of single crystalline silicon. Now, something so what are the characteristics of this ingot? First thing is what seed you selected. So, whatever seed you select will decide the orientation. The easiest growth is done along the 1-1-1 direction. That is just the property of silicon, because the surface energy of 1-1-1 is less than 1-0-0, and which is less than 1-1-0. This is what decides how hard it is to make other orientations. So, 1-0-0 is a little harder to make than 1-1-1, and 1-1-0 is even harder, which is why it is more expensive. If the nomenclature or orientation is not obvious to you, I would urge you to read up a quick primer on crystal orientation. This course assumes you know basic crystallography. So, you understand, for example, that the silicon has an FCC interpenetrated FCC lattice, and silicon are tetrahedrally bonded to other silicon. If this is not obvious to you, I urge you to read up, do this some extra reading. So, the doping is accomplished by adding controlled amounts of dopants, as we discussed before. Elemental phosphorus and silicon will react explosively, so this doping has to be a little carefully done, but that is a detail that we shall not cover here. An important aspect of this process is that oxygen does get incorporated in the crystal. The concentration of oxygen is typically 10 to the power 16 to 10 to the power 18. Now, this essentially means 0.01 to 0.01% of oxygen, and this mostly comes because the crucible that we are keeping the melt in is often made of an oxide, say a silicon dioxide or aluminum oxide, and the oxygen from that leaches into the melt. Electronically speaking, this does not prove to be too much of a problem, so we do not care about it. And happy side effect of this oxygen, it actually increases the strength of the crystal. So, the wafer is a little more resilient. So, the CMOS industry actually wants some of this oxygen in there. Another very important detail is the diameter of the ingot. As the silicon technology has matured, we have started growing larger and larger ingots, which is very important. So, how do we control that process? We simply look at the thermodynamics. Assuming this is a closed system where we are putting in some amount of heat because we are heating the crucible, some amount of heat is being lost, and the rest, the balance must be taken up by the latent heat of crystallization, which is what this expression tells you. Everything in this expression is either a geometrical factor such as the area or a material constant, for example, density and L. The thing that we control is the rate at which we are pulling the system and the amount of heat we are providing the system, which is Hn. So, controlling these two factors, we can actually dial in a certain area, assuming everything else remains the same. Looking at these expressions, you can probably appreciate why it was harder to make larger diameters, and it took certain amount of learning before we are able to make larger diameters. The rate of pulling for larger diameters must be extremely slow. So, this has to be a very slow and a very controlled process. The other thing is that for larger diameters, the difference between the heat that you are putting in and the heat that you are losing must be fairly large. What this means is that your thermal management must be very exact. This thermal management is easy to do when the amount of heat being supplied is small. It is much harder to do when the amount of heat that you have to supply is much larger. So, it has taken us some amount of maturity and time before we were able to develop control systems that can manage this process very precisely. Overall, as of today, the industry can routinely make ingots of some various standard sizes ranging from 25 mm to 400 mm. Most of this is done under inert atmosphere, partly so that the silicon remains silicon and does not become silicon dioxide by oxidation. the crucible must be made from some refractive material, because end of the day you are holding this very hot silicon melt. This is often made of silicon dioxide, but also lately silicon nitride. All right. With that, we end this part of the lecture. Next part of the lecture, we will go into details on how exactly the CZ growth happens, and how exactly we'll go over the concept like supersaturation, which actually explains to you how the crystal growth progresses. So, thank you.